This is General Physics 2, Week 10 AC. This is part 5 of the lecture, talking about DC to AC inverters. So let's say you've got a solar panel that's creating a nice amount of power from the sun. The natural output from a solar panel like this is DC, actually. But what if you want to be able to hook this up to things in your house that are designed for AC? Then what you need is this device called an inverter. You need a device that will take from DC and give you AC. The simplest of these, they're never made this way, but the simplest way of doing this would be to simply have a set of switches that would either connect the wires this way or would cross them and flip it the other way. So your output would be either positive or negative. It would just switch back and forth in polarity. That would be a simple way of doing things. But there's a problem with that. You can't directly apply that to devices that are intended for AC for the following reason. If you have something like that, what you find is devices are made, some of them use the peak voltage, and some of them use sort of the total power that comes out. And the devices that use the peak voltage from an ordinary 120 volt source, an AC source, the peak voltage isn't 120 volts. We've already figured that out. It's actually 170 volts. The total power, devices that use sort of the effective total power, those really depend in a certain sense more on the RMS value. What's the RMS that's coming from the power source? And the RMS voltage, of course, is supposed to be 120 volts. So some devices make use of the peaks, and some are making use of sort of the total amount of power. And here the trouble is you don't have a distinction between those two. They're equal. The peak voltage is this value right here. And so devices that are going to use that are going to pick off that value. But the RMS for this thing, now think about what that would be. Remember, RMS stands for root mean square, and you do them in the other order. So you take this waveform, square it, then take sort of the average value of it, and then you take the square root. So take this and square it. You've got some peak value here, and then down here it's the negative of that same peak value. So if you square this, what you're going to end up with is during this period of time, you'd have that peak value squared. What would you have during this time? Well, it would be this minus VP squared, but that gives you the same thing as when you had the positive one. Positive or negative doesn't matter once you square them. So you're going to get the same constant value of VP squared when you square this. Then when you take the average, well, the average of something that's constant is just whatever that value is. So it's just VP squared still. And then you take the square root, and that gets you back to VP. And so the RMS value of this is just the same as the peak value. There's no difference between those two. But these devices need a difference. Some of them are expecting 170 volts in the peak. Others are expecting the RMS value to be 120 volts. So these things want VRMS to be 120, and these want V peak to be 170. How can you satisfy that with a device that does it? You can't. But very quickly, people came up with a clever way of doing this, but still using simple switches, not trying to generate a beautiful sine wave. They generate what somebody stupidly named a modified sine. I assume they're trying to fool people. This doesn't look anything like a sine wave to me, but it looks to me more like a modified square wave, but it's called a modified sine. And what it's doing is switching back and forth, but it pauses in the middle at 0. So it looks very much like that, but here you have this peak value, So let's put that on the chart. Here is V peak. And then for a period of time, it's 0. And then for a period of time, it's minus VP. And then again, for a period of time, it's 0. And that then would complete one cycle in this waveform. So the hope is that this would give us a different number. We'd have a difference between the peak voltage and the RMS voltage for this. Now, the trick would be to say, well, can we adjust the period of time that it sits at 0 so that the RMS value is exactly 1 over the square root of 2 of the peak value, just like it is for a sine wave, just like it is for our normal power that comes in the wall. So let's see if we can figure this out. Let's imagine that we have a period of time here, T1 I'll call it. That's the time that it sits at this positive value. And then a different amount of time, perhaps, that it will sit at 0. And then we'll make it all symmetrical, so it'll sit at the negative value for the same T1. And then it'll pause at 0 for, again, the same T0 amount of time. And on it goes. Now, what we'd like to do is calculate what is supposed to be the ratio between T1 and T0 so that we get the right ratio between the peak value and the RMS value. So there's some VRMS in here that we need to figure out that'll depend on what these times are. And then we'll see if we can make the times right so that VRMS comes out to be 1 over the square root of 2 times VP. So how do we do this? Well, we have to calculate the RMS value for this waveform. So let's try it. The first thing we have to do, remember, is to square it. So this is our waveform. What are we going to get down here? So for the first period of time, it's at VP. Down on this graph, we're going to be at VP squared. So here is VP squared. I've rescaled the graph, so even though it looks about the same, it's VP squared. Then, for a different amount of time, perhaps for T0, this will be 0. 0 squared is just 0. Now, what about down here for this last period here? Then T1, again, that amount of time, but we're sitting at minus VP. Again, though, when we square that, we're going to get the same value. So this is going to go right back up to VP squared. And then it's going to come back down to 0 again. Now we have to compute the average. We have to get the mean. Remember, it's the root mean squared. So we've done the squaring. Now we have to take the mean, and then we'll take the square root at the end of that. So how do we get the mean of something that's switching back and forth between two values? Well, what you have to do is weight it according to how much time it spends in each place. So it spends a certain amount of time at this VP squared, and it spends a certain amount of time at 0. How much time does it spend in each place? So I'm going to compute a weighted average. So I'm going to find V squared average. This whole thing is V squared. Now I'm going to compute the average of that. And that's going to be one of these weighted averages where you take this value times how important is it? How much time does it spend there? Well, that's T1. That's the weight. And then this value, that's just 0 times its weight, T0. Okay? So, remember how to do this? So we'll take this value of VP squared, and then we multiply by the weight. How much time does it spend there? Well, in one full cycle, it's there for 2 T1. That's how much time it spends there. And then it's 0 for how much time? For 2 T0. That's the weight that would apply to the 0 term. And now remember, we're computing an average. And so what do we divide by? You have to divide by the sum of these weights. So we divide by 2T1 plus 2T0. So what's that going to be? Well, let's keep going here. This term, of course, is 0. And so we're going to get that V squared bar is going now to equal, well, what shall I do? Should we get rid of all the 2's, divide everything by 2? We're going to have T1 times V peak squared divided by T1 plus T0. Now, remember what we're after. Well, let's keep going, I guess. The next thing to do is to compute the square root of this thing. I'm going to rewrite this in just a little different form. I'm going to put the VP squared out here. It'll be a little easier to see what's going on if I do it that way. So now what we have to do is find the square root of V squared bar. To take the RMS, you first square it. That's what we did right here. Then you take the mean, that's what we did here, and then you take the square root. So now we're going to take the square root, and that's going to be the square root of T1 over T1 plus T0 times the square root of VP squared. That's just VP. Now, what is this supposed to equal? This is going to be VRMS. That's what we're finding. VRMS is this thing. So tell me what the times are, and I can tell you what the VRMS is, the times and the peak value. But now remember, what we were hoping was to get the same ratio that we normally get when it's a sine wave. And for a sine wave, VRMS is equal to 1 over the square root of 2 times V peak. Well, now just compare these two, and you realize, well, this square root of T1 over T1 plus T0, that's got to equal 1 over the square root of 2 for this to work right. Here's VRMS is this square root times VP. Here's VRMS is this thing times VP. So these two have to equal each other for this to work. So what we have then is the square root of T1 over T1 plus T0 equals, I'm going to rewrite that as the square root of 1 over 2. It's the same thing. Now you can square both sides, and what would you have? You'd have T1 over T1 plus T0 equals 1 over 2. And now to solve this, I think most of us would cross multiply. So this way you'd have 2T1, and the other way you'd have T1 plus T0. And that, I think you can quickly solve. Subtracting a T1 from both sides, you'll find that T1 equals T0. So having these periods of time exactly equal each other gets you just the right ratio, so that then you can plug in a device that uses the peak, like a computer. Most electronic devices actually just use the peak voltage. At least older ones do. TVs and such. Whereas something like a light bulb or a heater, a toaster, things like that, they depend on the RMS voltage. They're using all of the power all the time. So now, using this modified sign, you can plug in both kinds of devices. And you can set VP to be 170 volts, and then the RMS will be exactly 120 volts, and both types of devices will work correctly. Now, this is the kind of thing that was done years ago. Today, actually, electronics just keeps getting cheaper and cheaper and easier to do things. And so now most inverters actually produce a true sine wave. And it's not particularly more expensive to get that kind anymore, though at one time this was very common.